The newest, very recent modification or expansion to the modules in the program Micrometry includes a special type of tool that allows to create datasets for YOLO detection. Now, YOLO detection is different from standard datasets for machine learning implementations because you need to follow a very special format. You start with images, and rather than subsampling a specific area inside of those images and storing them, discarding the entire information from the rest of the image, you rather save the original image and use a normalized version of boxing areas to specify in which points the labels are located and how wide the boxes have to be. The expansion for the YOLO implementation is a very powerful one, because it allows to quickly create datasets that can be moved into the object detection algorithm. So let me show you how to run the YOLO datasets. We start, as usual, by going to the terminal and activating our environment. In here, we can type Python, then main.py, and this time I'm gonna type -h to get the help with the parameters that we can use. Notice that we can still use the camera index to represent the index of the webcam that represents the camera that is connected to our microscope. Resolution is the same, it hasn't changed, but now we have an additional flag that is called KC. And KC stands for Keep Classes. What happens is that whenever you create a dataset, you get the option of preserving the classes that you had previously specified that have to be built and stored into a TXT file and placed inside of the labels subfolder. By default, this value is set to 1, which means that these classes are going to be kept, because it is assumed that every time that you use it, you're just adding to the elements that you already had before because they're part of the same project. If you need to start a new project, however, KC should be set back to 0. So this is how the program works. There is a TXT file called predefined classes in there that contains NOBI values of labels that are going to enter the program YOLO. These are things that will hopefully never appear on the microscope, but are going to be included in order to create a comparison for the confusion matrix of the model when it starts learning. So in here we have two folders which are going to be copied and pasted inside of the YOLO detection algorithm at the moment of training. So you are not going to modify their names, you're just going to copy them and then you're going to paste them inside of whichever folder you decide to. The first folder contains the original images. Here, the important parameter is the name of the files, so you should not modify them. You should let the algorithm work with whatever default values it gives you. Each of these images contains information, spatial information that is distributed in a two-dimensional space on where the organisms are. And that information is found inside of labels. For each image, there is one label stored as a TXT file that contains information on the category, position in X, position in Y, width and height at which the particular element that belongs to that category is found inside of the image. Notice that these values are never bigger than 1. And the reason is because these values are normalized. Let's see how we can add elements to our dataset. Now we can type Python, main.py, ci in my case is the index 1 for the camera index. The resolution I'm going to set it to 0.8 and I want to keep the classes. So I'm going to press enter. And once I'm here, I can start annotating right away. Compared to other applications in Micrometry, notice that this one doesn't have any buttons at all, other than the big annotate button at the top left corner. And the reason why is to simplify the process. We don't really need more than that. If I zoom in into my charismatic friends here, the rotifers, which are actually the same specimens from the previous tutorial, I can freeze the screen by pressing the spacebar. I'm pressing a spacebar right now, and I'm trying to keep this guy in view. There it is. And notice that the annotate tool has disappeared. Once you freeze an image, it is assumed that you're going to start adding boxes. If I click on annotate, the program still freezes the image. So freezing and annotating are the same in this program. I can click and drag my square. And once it's been selected, I can give it its label, which is a rotifer. Here the program will calculate everything else. I press enter to confirm the name of the tag, and I can move to the next one. This right here is also a rotifer. So I call it rotifer, and this one is a third one. They're all rotifers. But oops, I made a mistake. This label is not right. What I can do now is to use the right mouse button. By pressing it down, I can hover my mouse on top of whichever label I want to eliminate. And once I'm there, I can lift the right button of the mouse and the box has disappeared. This is useful in two scenarios: when you make mistakes with the label, but also when you mistakenly set the box at a height that doesn't include all of the information on the specimen, which is essential for object detection. So this is called the rotifer, and I don't like it either. So I right click on it and I can remove it. I can remove everything. So let's keep it right. I set this rotifer value here, rotifer and rotifer. Once I'm ready and I'm sure that the labeling is appropriate, I press D for done, and the program will save the information into their particular folders. This guy is begging for another one. I'm gonna set the box here. It's another rotifer. And it turns out that rotifers are actually quite hard to get because they really like hiding most of their body parts. So sometimes it confuses the model. I'm starting to consider whether or not it may be useful to separate it into two classes: rotifers feeding and rotifers otherwise. I'm gonna press D for done, and then I'm gonna close the program to avoid temptations. Now that I have this, I'm gonna go back to the images folder, and if I go all the way to the bottom, I should see my rotifers there. They're right there. It's the very last image that I took. The image is number 133. They are sequential. And they're sequential so that we can erase them from the labels and from the images if we decide to. And if I open one of the labels, you will notice that the two rotifers both belong to the same class, which is 22, and they have their different coordinates inside of this image. So let's suppose that I'm done annotating my dataset. What I do next is copying these two folders and moving them into the same folder where I have the YOLO algorithm. There is a really nice GitHub repository that applies the YOLO algorithm that comes from a group called Ultralytics. In here you can store the data directly. I call this data July 2024, and then you can see the images and the labels in there. To train the model, you can simply refer to that particular folder and start the training process. I will leave a description to this repository so that you can download it as well, and there is plenty of really good tutorials out there if you decide to go for this particular model. Let me show you how the model looks like actually. If I open the command prompt, I can activate my environment called YOLO environment, and now I can test my YOLO.py. What's happened? Okay, here I need to type Python, and I can test the YOLO.py, which is the model that came out of the training data that you just saw me annotating. It's doing some wizardry behind the scenes in the backend, and once it's done, you can see that the model successfully, learns to recognize rotifers, with a good confidence level. It's not perfect. It's not catching all of them because some of them are quite blurry, so I need to expand the dataset, but still, it's doing a pretty decent job. This is the small version of the model. It doesn't have as many parameters, and I presume that it has really good potential to create very good approximations with very real applications in science and outreach.